You're listening to Let's Talk Creation with Todd Wood and Paul Garner, the creation show where we learn, grow, and worship.
Well, it's great to be back for another episode of Let's Talk Creation with Paul Garner and Todd Wood. I'm Paul Garner.
And I'm Todd Wood.
A reminder to all our listeners to subscribe, share, like our episodes, all of that kind of fun stuff. Leave us a positive review. We're very appreciative of all that you do to support us. Tell a friend about us. If you've really been enjoying the podcast, then do share it with others. Now, Todd, today's episode, we're going to be going back to one of our occasional series that we've got running. We've got several going at the moment.
It's hard to keep track sometimes.
It is. I hope that our listeners are kind of sticking with us on these series. And I think on our YouTube channel, you can actually go and look at the playlists and you can get all the back episodes in each of those series. So if you want to catch up. Today, we're going to be thinking again about radiometric dating. And I guess we ought to, for those of us that are just joining us in this episode, we ought to have a bit of a recap. So just to remind listeners about what radiometric dating is, it's essentially the method, or rather the kind of set of methods that geologists use to date the Earth's rocks and minerals. It relies on the radioactive decay of naturally occurring radioactive isotopes. They decay over time. An unstable radioactive parent isotope decays often through a series of intermediate steps until ultimately a stable daughter isotope is produced. And this decay happens with a predictable half-life. And so you can use this, in effect, as a kind of geological clock to estimate the age of rocks and minerals. So if we know the amounts of parent and daughter isotopes in a particular rock sample that we're studying today, and if we know that the daughter is derived from the radioactive decay of the parent isotope, and if we know the rate at which that happens, if we know the rate of decay, then you can use all of those things to sort of estimate the age of the rock or mineral sample. So that's basically how it works. And we know, of course, that radiometric dating yields ages of millions or even billions of years, typically, for rock samples. And of course, for those of us that accept the biblical teaching of a young Earth, that's a significant challenge. And so in this series, we've been trying to dig into the whole topic of radiometric dating and to try to understand these methods and how they work, and to explore whether there's an explanation for these vast ages that radiometric dating methods give us within the young Earth model. So that's kind of what we've been doing. So Todd, remind us some of the topics that we've already covered in this series.
Right. Yeah, I got a list here so that I don't forget anything. So this has been maybe our longest running intermittent series, I think. We started this back at episode 26 with a intro and overview. And then episode 35, we had Ben Clausen on to describe exactly what radiometric dating was, give us sort of the technical details of how it works and what it's about. Episode 40, we introduced the RATE project, Radioisotopes in the Age of the Earth, and you might remember that as the big creationist project a number of years ago, where creation scientists from a number of different organizations sort of teamed up to try to solve the mystery of radiometric dating. And they've done some really interesting research that we then wanted to evaluate. So in episode 44, we talked about critics of rate, and we kind of gave our own reaction. And I think mostly what we just said was that there's a lot of really interesting stuff here, but we're not done yet, that there's still more to do. There's still more work to do. So it wasn't, we weren't hypercritical, but we weren't, I guess, naively optimistic about what was happening there. And then we took a long break. Long enough that people started asking us, are you going to do more on radiometric dating? So episode 75, we had Russ Humphreys in to talk about some of the rate research that he did with excess helium. And that was one of the more technical episodes. We talked about digging cores out of the crust and looking at counting helium atoms and how diffusion works. It was complicated. So definitely if you're kind of new to the podcast, or if you are still not quite sure, go back to the back catalog there and check out all of those old episodes. They're all still on YouTube and all the podcasting platforms. You can check them out there. All right. So if you're a little confused by this, fear not. There are remedies there. Now, this episode is, I understand, Paul, a little different. In that we are not going to talk directly about the radiometric side of dating. We're sort of going to ask another I think this is a really interesting question. Do other methods of assessing age, geological age, do they all agree with the dating methods, right? So do they agree with the radiometric dating methods? And that's a fascinating question, because you would think if the Earth is really old, then all the sort of methods should all just give you the same kind of answer, right? If you start thinking about, dating by other techniques, all the dating methods should roughly line up. So, yeah. So that's the question. So,
yeah,
we're trying to figure out the age of the Earth. And the age of the Earth, Paul, what do you got for that? And I know what you think, right?
Right.
But
okay.
the conventional model puts the age of the Earth where?
Yeah. So according to conventional radiometric dating, the Earth is about 4.5 billion years old. The visible part of the fossil record, what geologists refer to as the Phanerozoic, goes back to about 539 million years ago. Now, we probably need to put this all in some kind of perspective, because when we talk about these enormous ages, it's very hard, I think, for people to visualize what we're talking about. It's almost unfathomable. Geologists often sort of liken the history of the Earth, the 4.5 billion year history of the Earth, to a 24-hour day, to try to sort of bring it down to something that people can really grasp. So if we imagine that 4.5 billion years is kind of compressed into 24 hours, beginning at midnight, the base of the Cambrian, which is the beginning of that visible part of the fossil record, where trilobites show up, that doesn't begin until 9:10 at night. So we have this enormous long sort of period before we get to, the first abundant animal fossils. And then, if you think about the age of the dinosaurs, the Mesozoic, that runs for about 1 hour, from 10:41 p.m. to 11:39 p.m. And the first human-like fossils don't appear until about 20 minutes later. So that's about 90 seconds before midnight. So that kind of gives you some idea of the kind of time spans that we're talking about, and how it looks if you kind of laid it out, in a 24-hour period.
Yeah.
So it's a huge amount of time. I mean, it's just almost incomprehensible to the human mind. And this is why some geologists refer to this as deep time, to sort of emphasize just how vast these time spans really are. And so we thought that it would be, as you were saying, helpful to look at some other types of dating methods, because this vast time span is largely derived from radiometric dating. But there are other ways that we can get clues about, timescales, Earth history timescales, using clocks other than radiometric dating. And so we thought it'd be interesting to have a look at those and see what they can tell us. And in order to do that, we are joined today by a very special guest, a geologist, Dr. Monte Fleming. So Monte, welcome to the show. It's really good to have you.
Thank you. It's good to be here.
Monte, after a couple of false starts, we've tried to schedule this episode previously, and for various reasons it didn't happen. But it's so good to have you here today, and to be able to talk to you about all of this. I first came across you, Monte, because you had written this book, which is titled "Stories About Earth's History: A Geologist's Descent from Deep Time." And when I read this book, I thought that would make a great couple of episodes for our podcast. So we were keen to have you on. Monte, why don't you begin just by telling our listeners something about yourself. Just give them some idea of your sort of bio, your background.
I'm an assistant professor of geology at Loma Linda University. My research, done some really interesting research projects. One in Peru, it was the Miocene Pisco Formation, and it's in a really incredible fossils down there. The sedimentology is interesting, but the fossils are really extraordinary. Lots of whales and other things. We'll talk more about that later. Another really interesting research project was in Arizona. Arizona's famous for these large mesas that just stand, sticking out of the desert. Well, we discovered that on the tops of several of these mesas, there were actually these giant potholes. When I say pothole, the scale may not invoke the scale very well. These are the biggest ones were about 50 feet deep and 100 feet across.
Wow.
15 or so meters deep and 30 or so meters across. And so the question, of course, is how in the world do you get these huge pits in the bedrock at the top of these mesas? And so that turned out to be a really interesting project. It looked to me like there's a significant amount of water in the past running through that area. And then more recently, I've been working I built a flume here at Loma Linda and built a sediment feed. And I've been working on reconstructing the conditions under which various sedimentary structures form. So that's been some fascinating research. I started that at the University of Minnesota in St. Anthony Falls Laboratory, where they do a lot of that.
Okay. Yeah, okay. I've been to the St. Anthony Falls lab. I was there at a GSA, Geological Society of America meeting. We had a kind of trip out there to see the laboratory. Yeah, fascinating. So you've got a flume there at Loma Linda now. That's really interesting. Yeah. Oh, that's great. Yeah, you're doing some fascinating research there, and we could talk about any of those topics, and maybe we'll have you back to talk about some of those other things as well. But today we wanted to kind of dig into some of the themes of your book. We will put the details of the book in the show notes, by the way, because I'm sure many of our listeners and viewers are going to want to get a copy of this. Where do we begin? So I thought in this episode, we would probably talk about erosion. We'll focus on erosion. One of the things that I was very struck by as I sort of read your book, right at the beginning of the book, you talk about, again, trying to bring to people's attention, really how vast these time spans are. You talked about how even tiny, insignificant processes can have enormous effects over very long time spans. And you gave a few examples. So you mentioned here, your hair could wrap its way around the Earth's equator 17 times in the 4.5 billion year proposed history of the Earth. A snail could make 186 round trips to Pluto and all this kind of stuff. So the point you're sort of making there is a lot can happen in intervals as long as the ones that, we infer from radiometric dating. Then you go on and you sort of apply this to geological processes and particularly erosion. I wonder if you could sort of begin to unpack this for us, and maybe we should begin with coastal erosion, because I think all of us are familiar with news reports where you see coastal communities that are being adversely affected by coastal erosion. So just begin by sort of helping us to understand the kinds of rates of erosion that are happening around the coast, say, of North America.
I suppose to put this in economic terms, because that's how people tend to get affected by it regularly. It costs about $500 million in property loss each year in just the U.S.
Wow.
And if you search, you can. There are a lot of images online of buildings falling into the water. So this house was this was a hurricane in Florida. Another house that got damaged, I think, by the same hurricane. You can see all the rubble at the base of this cliff. That's a telltale sign that the stuff has fallen off. And also you can just see, like, if you just look at these cliffs, you can tell that this is these sedimentary layers have been there for a while, but the ocean just keeps kind of cutting away at them. This is Alaska, and you can see these blocks that have just fallen off recently. Another place where between January 2 and January 24, the sea took part of the road. And it doesn't just happen in the ocean. Large lakes are also, and well, not just large lakes, but there's some pretty dramatic coastal erosion in the Great Lakes here in the U.S. This is Lake Michigan.
And I'd encourage, if you're listening to this on the audio stream of the podcast, come along to YouTube and see some of these dramatic photos that Monty is showing us here. You know, we're seeing these buildings which are sort of teetering on the edges of cliffs and roads that are being eaten away by the sea, and on the shore of Lake Michigan here. So do be sure to come and check out the YouTube video to see these amazing photos.
Well, another place where this gets interesting is lighthouses. There's a company that has moved 6 lighthouses on the east coast of the United States because they're nice tourist attractions. What's interesting about this is that if you Google the rate of coastal erosion in the East Coast, it actually matches pretty well with the lighthouse moving data. I think if you Google it, it comes out to about 1 meter a year. And if you look at the lighthouses at each of the places where these lighthouses were moved, it's about 2 feet per year. This is Southeast Lighthouse in Rhode Island. That one, you can see where the cliff is in this image here. And that cliff just kept getting closer and closer to the lighthouse, so they had to move it. North Truro, another lighthouse that had to be moved. Nauset Lighthouse, that one had to be moved.
I find it amazing that you can pick up a lighthouse and move it further inland. This just seems an extraordinary engineering feat to me, that you can move these buildings. But
it's great. They dig down under it and put they build a really solid platform under it, and then they just pick the platform up and just inch it just very slowly over the course of sometimes weeks or even months. They'll just kind of inch it a few hundred meters away from the shore. Cliff collapse and beach erosion on the West Coast. I think if you Google it, it's a few centimeters per year on the West Coast. We're not quite as bad off as the East Coast is.
Why is that? Why is it not so rapid on the West Coast, Monty?
I think, the rock type that the waves encounter matters a lot. And here in Southern California, we have a lot of the beaches that I've been at. It's pretty consolidated lithified Miocene material, for example. Yeah, a lot more rocky cliffs, I think. And then also there's kind of the coastal cities on the West Coast don't tend to be down at sea level quite. There are, but the coast tends to rise up quite a bit pretty quickly. Mm. And then there's we'll get to the marine terraces in a bit too. I want to talk about that. And that actually tends to push the sea out over certain time frames. All right, so this is an interesting website. You can see that they've been cataloging data here on the California coast. Red is high erosion area. If I click there, it's 0.85 meters a year. Orange is not so bad. That's only 0.1 meters per year. Click on San Francisco, 0.14 meters per year. But those rates do add up over time, as we'll keep talking about.
So on the East Coast, then you've got maybe 1 meter of erosion. Did you say a year? So sort of 3 feet or so.
Right.
Bit slower on the West Coast. Not quite such high rates, but still, these are quite dramatic. It's fast enough that we're having to sort of move these buildings like lighthouses further inland.
Yeah, they've never had to move a lighthouse closer to the ocean.
Right. Sure. So what can we infer from this then, from timescales? We said a moment ago that, even very what seem like tiny sort of insignificant processes add up over time. So how does this add up over time? I mean, what can we infer from this?
It's interesting because this one is not even an insignificant process. This is one that would affect your house in your lifetime.
Yeah.
If you lived near the beach. I have a friend he was on the shore of, I think it was Lake Michigan, when he was in college, and they were tossing rocks. They were sitting on the shore tossing rocks into the lake, and someone came out and just got irate, yelled at them because they were throwing his lawn into the lake, and he was already losing a lot of it. But so if we take these values, meter a year, several centimeters per year, and then kind of extrapolate what should happen over a few million years, the United States is a few thousand miles wide, and it would only take about a little over 4 million years if sea level didn't change and if the ground didn't move and any of that. It would only take about 4 million years to just kind of level everything. Now, again, that is simplistic because there are these other factors in play. But yeah,
but even so, I mean, that is remarkably rapid.
Well, right, 4 million years is a drop in the bucket at deep time.
Yeah. So we would need a lot of compensatory kind of processes to make up for the fact that erosion rates are so rapid, because you could effectively completely consume the continent in 4 million years, which, as you say, is nothing in the radiometric timescale. So yeah, that's remarkable. So it seems there is a time conflict here when we consider the dates that we infer from radiometric dating.
So 4 million years is just 2% of the supposed 200 million years that the continent of North America has existed in its roughly current configuration, according to popular geological thinking. But what's even more interesting is that the continental shelves are only a few kilometers to a few tens of kilometers wide around North America, around the continent. And so that means that very little coastal erosion has actually happened in the history of North America. And it's not just North America. This is worldwide. This applies to everything. It's just that
just to unpack that for our listeners, because I think what you said there is quite important. So when you talk about the continental shelves, the continent doesn't kind of end where the ocean begins. The continental crust extends outwards under the ocean for some way before you actually get to oceanic crust. So we can estimate from that how much coastal erosion has actually taken place.
Right. If you can see my screen here, so the scale is 70 kilometers right now. And so you can see that there's significantly less than 70 kilometers of shelf right here off the California coast.
So that's the light blue area.
Right.
And then it goes down the slope into deeper water.
Right. So if you, and the deeper water is, on average, it's about 4 kilometers deep.
Mm-hmm.
And then the continental material comes up, and that's about 800 meters tall on average. Yeah, if you look all around the continents, you can see that the shelves on the east are wider, which that makes sense because the erosion rate is faster on the east coast. But still, that's just let's see what the scale is. 100 kilometers, less than 100 kilometers in many places.
So we can't simply assume that North America was once much, much larger in order to account for all of this erosion. We can actually tell from the width of those shelves how much erosion, what the kind of maximum is that could possibly have happened.
Right. So, of course, people have brought this argument up before, and somebody sent me when I was talking about this earlier, somebody sent me a Rational Wiki, and a quote from Rational Wiki. They said, presumably the argument from coastal erosion is meant to imply that all the land would have been eroded into the ocean by now if the Earth were old. However, land lost from coastlines does not necessarily just disappear, but is often deposited elsewhere. For example, Rye, East Sussex, town in the same country as Beachy Head, was once an important port, but is now inland. Similarly, Cape Cod, entirely of sand and gravel, a glacial moraine, sometimes loses substantial amounts of shoreline in some places, while aggregating large amounts in others. Likewise, land can rise above the ocean, such as Surtsey, or land raised by tectonic plate colliding. So they talk about two processes to account for all of this. One is redistribution of sand around the world's beaches, and the other is uplift of the continents. I want to look at the claim that sand from one beach is distributed elsewhere. That one's interesting. So in the 70s and 80s, there was a large survey that indicated that about 70% of the world's sandy beaches were experiencing erosion, 10% were experiencing accretion, and about 20% were stable. This is a more recent study on satellite imagery from 1984 to 2016, and it found that 24% of the world's sandy beaches are being eroded, 28% are growing, 48% are stable, and on average they found a net gain of 0.33 meters per year over the past 30 years worldwide. So that makes it look like more sand is actually accreting on the world's beaches than is being eroded away. So that's interesting. So, so is Rational Wiki right? Are beaches basically stable over long periods of time? Should we just stop annoying people with this non-existent problem and pack our bags and go home? So I thought, well, let's not get too hasty. Let's dig into the study a bit. So first, it only reports on sandy beaches, and a lot of the images that I showed previously were actually cliff erosion. That's what causes a lot of the economic damage. I mean, sand does too. They have to, here in California, they like to keep the beaches nice for tourism, so they dump a lot of sand out there sometimes. That's very expensive. So one thing to notice, though, is that the study only looks at sandy beaches, which is about 31% of the world's ice-free shorelines.
Mm-hmm.
So, and it doesn't account for sea cliffs. And that, again, that's where a lot of economically troublesome erosion happens. And sea cliffs only erode. They're not going to grow out into the ocean. Uplift can create new sea cliffs. We'll talk about that in a bit. But another really important thing about the study is that they're looking at satellite imagery, and the resolution of the measurements is only about 0.5 meters. So you could get erosion at a rate less than 0.5, which is considerable. It would still come up as stable in the study. So the fact that they say that so many beaches are stable, I think we need better resolution to say that.
Yeah. And the average they mentioned, the average they mentioned was 0.33 meters of growth, which is less than their actual resolution. So in fact, the average is indistinguishable from erosion or from stability.
I think though, so if you were to, if the best you could do is 0.5 for resolution, and then you put a bunch of data together, you could get 0.33 as an average.
Well, yeah, but you wouldn't be able to know for sure if that's growth, erosion, or stability, because it's too small to be detectable.
So this is where the green is accretion and the red is erosion. Okay. So first, notice that some of the accretion is not happening in the ocean's beaches. It's happening in bays and seas. So like, up here, there's a big green area that looks kind of far away from the ocean, and it's the Caspian Sea. And that's getting included in the averages. Up here in the Hudson Bay, there's a bunch of rivers that dump a lot of sediment into the Hudson Bay. And so, again, that looks like there's a lot of accretion, but it's not really happening shorelines of the world to speak of. It's happening up there in Hudson Bay. So next, let's ignore China and the Persian Gulf for a minute, because there's a lot of accretion going on right there. Let's look at the areas of accretion that are happening along the ocean's coasts. So several rivers dump into Hudson Bay, like I mentioned. The Hudson, Potomac, St. Lawrence, and other rivers dump into the Atlantic in the northeast in this one kind of dark green spot. The Mississippi and Rio Grande dump sediment into the Gulf. The Savannah River in Georgia and South Carolina dumps. There's another green spot on the coast there in South Carolina. The Ganges, you can see the big green spot where the Ganges Delta is. That's the biggest delta in the world. There's a big green spot by the Mahi River in India. The Rhine and Elbe rivers dump sediment into the North Sea. And also there's been a lot of land reclamation in the North Sea, which we'll also get to in a minute. So again, ignoring China and the Persian Gulf, the vast majority of sand accretion along the world's beaches can be accounted for by river deltas. And so back to the argument is that the sand gets redistributed, but if you look at the actual data that this study shows, what we see is erosion, significant erosion along a lot of coasts, some accretion where there are deltas, and that's not going to lead to a stable worldwide system. That's the deltas are going to keep growing, and the places like the more arid places like Southern California coast or the some coasts in Australia or Africa, they're going to keep getting eroded away. Another point is that sand doesn't just get shuffled around. What actually happens is that it gets, like here in California is a good example. Sediment gets dumped out to the beach by rivers and streams, or at least, it used to before we diverted it all to irrigation. That would then get pushed up the beach gradually by the longshore current and by the wave action, and then it would find a submarine canyon and disappear down to the deep seashore. And so the sediment, it has a half-life once it gets to the beach. It's not going to just get redistributed indefinitely. So back to the article. What about China and the Persian Gulf? There are huge amounts of accretion in those areas, but it's all anthropogenic. Think about how much land United Arab Emirates, Bahrain, Singapore, China, and these other countries have reclaimed. It's thousands and thousands of square kilometers. And that all shows up as accretion in the study. Again, I'm skeptical that that there's actually net accretion going on if you take the human fingerprint out of it.
Which, if you're going by the kind of conventional timescale, that human influence is a very recent innovation. So it's it can't account for the stability of the continents over long timescales if it's something that's only happening very recently. Yeah.
And I also think that Netherlands has reclaimed an awful lot of land as well, and I think there's a big green spot right by that land reclamation. Okay, so to summarize my response to the everything equals out over time argument, I would say that sand is gained in some areas locally due to river sediment input, but the general trend is erosion, and neither river delta deposition nor coastal erosion appear to have been going on for millions of years. When you look at sea cliffs, when you look at other types of shorelines, not just sandy beaches, and I think that when we do, we'll see a clear trend of erosion, as has been noticed by humans for a long time. The exception to that would be uplift due to earthquakes. The shore actually got pushed out in the Christchurch earthquake in New Zealand, popped the land up a little bit and gained a bit of coast. And then in order to get a good handle on what's actually going on with the study's data, they have to remove land reclamation from the data. And also we just need better resolution data, I think. The other objection to coastal erosion argument is that uplift accounts for sediment and other materials lost from the continent. And this is partly true. Okay, so this image here, this is a great image of marine terraces. This is San Clemente Island off of California. It's one of the Channel Islands. And you can see there's a terrace with a road going on it right next to the coast here. That used to be a beach. And probably 120,000 years ago, according to mainstream geological interpretation, the beach used to be way up here at the top of the island, and that island got pushed up relative to sea level. Sometimes the sea level drops, sometimes the line goes up. And that island got pushed up relative to sea level in multiple episodes until the beach is now several hundred meters out from where it used to be.
Okay, so we have this whole sort of series of what look like steps, going up from the ocean inland, and you're saying these are wave cut platforms that were once at sea level. These were once cut by the ocean. So these are kind of raised beaches, and we've got several of them. 5, 6, more of them here. That's really interesting, and that pushes the sea out in effect. So there's Yeah. So, theoretically, you could just keep doing things indefinitely, and it would keep the coastline in roughly the same spot if your factors evened out. So I really wanted to understand the development of the marine terraces in California in terms of coastal erosion, uplift, and eustatic sea level change. So I took a look at recent coastal erosion data from Northern California in an area with prominent marine terraces. This area right here. This is Google Earth, and so it's hard to see clearly what's going on. But you can see a big terrace here, another terrace here, and this should be that same 120,000 year terrace as we saw in the previous. So to give some background, so in California, we have the Pacific Plate and the remnants of what was the Farallon Plate getting subducted under the North American Plate. And as that happens, it creates these faults and these earthquakes. The land gets pushed up kind of sporadically. Which is one of the reasons why the terraces tend to be stepwise and not a smooth transition. So I looked at an area near Mendocino. Now this is the cross section of how the terraces form. So I looked at this at an area here, and you can see this is what the kind of the profile of the coast looks like. Saw that, okay. And so there was a study in Northern California. And they came up with this diagram. And so you can see sea level change off to the right, and you can see the surveyed profile of the marine terraces off to the left. And they are correlating the marine terraces with specific points in the sea level curve. And so what's happening here is you have
a coast and the sea cuts into it, the coast pops up, sea cuts in again, coast pops up, sea cuts in again. Okay, so I wanted to see if this diagram made sense, so I started doodling on it. I measured the heights of each terrace, measured exactly, the year and the height of each sea level change. That's measuring the year, measuring the height, and it came up with all of these numbers. That's meters per 1,000 years of uplift. That's the 1,000 years, number of thousands of years, the actual meters of uplift that would have happened. And doing this with the diagram, it actually nailed it. So that it shows that their diagram was actually quite good, even zoomed in perhaps closer than they thought anyone would ever zoom into it. All right, so one takeaway is that because the sea level is only thought to have been close to its current level for a few thousand years over the last 300,000 years, most of the coastal erosion for this period would have happened down on the shelf and not at the current coastline. Another takeaway would be that if the diagram is correct, then uplift rate over the last 300,000 years is roughly steady. So that adds coherence to the story. So at least for part of the Pleistocene and the Holocene, it looks like the mainstream geomorphological narrative of the California coast is fairly coherent. I would say one caveat is that more of the shelf should have perhaps been eroded away, but I think you could posit enough sediment redistribution to cover that perhaps. So again, back to that question, should we just admit defeat and stop claiming that science supports the historicity of the Bible? And I want to address that issue before we dig into coastal erosion more. So how should we react to the hypothetical scenario that not just 300,000 years is coherent, but also 50 million years would perhaps be coherent? Because that's the California coast has changed considerably before 50 million years, according to the standard geological narrative. And the reason I bring that up is because it would be easy for someone to pick up my book or another similar argument, and then run into a knowledgeable geomorphologist. That person might be able to give them a coherent story for the last 300,000 years and assume that the story remains coherent beyond that. And it would, it could sound convincing, or someone might pull up that study on the erosion and accretion data that we just looked at and say, see that, at a casual glance, that debunks the argument. And so, two things that I want to talk about. One, in relation to that, one is what I would say is the nefarious use of nuance to supposedly dismantle the core of what is really a robust argument.
Mm-hmm.
And in this case, redistribution of sand and uplift are nuances, but they don't solve the problem of coastal erosion for deep time. And the second would be that sometimes we actually run into something like this. I mean, the reason you're doing these episodes on radiometric dating is that it actually is a problem. Sometimes we run into things like radiometric dating or the heat problem. And, should we let something like that destroy our faith? And, there's abundant evidence from archaeology in support of the biblical text. There's abundant evidence from the text itself. And so we have to, when you compare radiometric dating with all this other stuff, it starts to really shrink in importance. It occurs to me in a lot of the discussions that I've had that the party line in evolutionary thought is all of the evidence fits our worldview. Now, to be fair, not everyone believed that. Like Christopher Hitchens, for example, admitted that the fine-tuning argument was evidence for God. But it would be nice if, I think we could have a lot better dialogue if it were acknowledged that, no, actually, reality is rich. There is a lot of data that nobody understands. Okay, so back to the terraces. It gets interesting when we take a step back and look at more of the supposed history of the coast. This is the sea level curve for the Phanerozoic. And so you can see that sea level has been dropping for about 50 million years, according to this graph here. It's been dropping for 100 million, but I'll mention but just 50 because of the history of the California coast. So this is the coast of California 130 million years ago, according to reconstructions, and B is what is now the coastal range. Here the coastal range is C, and so you can see that that's 50 million years ago in the Eocene, and you can see that then got accreted onto the continent, but it's been subjected to erosion for maybe 50 or so million years. So that gives us a number that we can use to calculate. This is the northern coastal range now. You can see where it ended up, and this is a topographic map of California. So you can see that when sea level was 100 meters higher it would have really affected the Central Valley. It would have really affected the Los Angeles area. It wouldn't have had as much of an effect on much of the rest of the coast. For most of the coast, a few tens of millions of years of erosion with rising and falling sea level, it's a reasonable way to try to reconstruct the mainstream story. So these are numbers that I pulled off of the California Coastal Erosion website, and these are the heights and ages of the terraces. We have 17 kilometers of shelf, roughly, available. We have an erosion rate of about almost 6 centimeters a year. That's almost 6 kilometers per 100,000 years. The shelf angle, I don't know what it is exactly off California, but it's roughly 0.1 degree worldwide. And we'll give it a 50 million year time period. So the time necessary to erode 17 kilometers would be about 291,000 years. The minimum height that the shelf could be eroded back to the same location would be about 30 meters. And that is because of the slope of the shelf. So if you just do trigonometry, the tangent of that tiny angle, it's going to come out to about 30 meters. So that gives us 171 available cycles of eroding in, raising up, eroding in again, raising it up, eroding it in again, raising it up. Now that's absolute best case scenario. And in order to do that, in order to keep the coast roughly where it is, it would still require 5,000 meters of uplift just since the late Jurassic. Sorry, since Eocene. But the actual rate of uplift is more than that. If you account for the actual rate of uplift, you end up burning through the entire crust. All almost 20 kilometers of crust to get to where we're at, right?
Right.
Okay. So you can see where the problem is.
So what you're saying is, we have these coastal erosion rates. If you don't take any other factors into account, are going to consume the entire continent in 4 million years. But we do have these other sort of counter arguments that sometimes get brought up. About the redistribution of sediment. So sediment that's eroded in one place just gets dumped somewhere else. So overall, the continents are stable. And then we've got this argument about earthquakes causing uplift that, in effect, pushes the sea out.
Right, just cancel out the
just cancels out the coastal erosion. And what you're saying is when you actually crunch the numbers, when you actually kind of really dig in and look at the details, these don't compensate for the coastal erosion rates. The coastal erosion rates are just too high. So there still is this big time conflict. Have I got that?
So to restate my last point, in other words, it would take you'd have to uplift the entire crust of California to keep the sea where it is right now. People don't really know how the crust formed. There's a lot of models, and when you have a plethora of models, it probably means it's not well understood. I'll just read a couple of these quotes. Opinion on how Earth's earliest continental crust evolved is strongly divided. These are all from peer-reviewed articles. More than 3 decades after the work that established the base of crustal growth concepts, our understanding of how continents grow and differentiate still remains somewhat obscure. This is the age of the continental crust, roughly. And they've done this taking data from sections, so it's better data than just surface data. And you can see that most of the crust formed before the Phanerozoic record. And this is the crust that's supposed to be cycling to replace what's lost by erosion. But if we look at this, we can see that there hasn't really been cycling of the crust. This is a fascinating quote. Finally, regardless of sampling approach or geographic scale, igneous rock quantity does not decrease exponentially with increasing age, as predicted by most basic models of rock cycling. In other words, the evolutionary model, if you start thinking about erosion, you need to posit a significant amount of recycling of crust.
Right. So what you're saying is, you would have to uplift the whole thickness of the crust,
right,
to maintain the coast of California where it is. We don't see evidence of that. Are you saying that we only have evidence of at most kind of one cycle of uplift rather than multiple cycles, which is what we need to see?
If you go back to this slide, I'll go back to this slide. So we don't even have evidence of one cycle of uplift because that old crust is all there. There's a story about how this crust formed based on these radiometric dates. There's a burst of formation here, there's another burst of formation here, and we still have all of that story preserved. And if we look at the East Coast, it gets worse because the erosion rate's faster and there's not all of the tectonic activity. So just a quick thought experiment. Let's say the East Coast erodes 10,000 meters, and then it's uplifted 20 meters over and over again relative to sea level. How much uplift do you need in 200 million years, because that's how old the East Coast is supposed to be, to keep it at roughly the same location? Let's assume a meter a year of erosion. That's 400,000 meters or 400 kilometers. And that's where the International Space Station orbits, right? The crust is only 30 kilometers thick in the east. And so to erode 400 kilometers of crust, you have to reform the crust 13 times in 200 million years. That's once every 15 million years.
Yeah.
In other words, you shouldn't have crust older than 15 million years on the East Coast, if that's what's happening. And
this is very interesting. So they're really, the time conflict sort of gets greater, I think, the more you sort of dig into this.
And, one just kind of interesting aside, this is the sea level curve over history back to 30 or so million years. And it's interesting that we have such intense variation in the recent past and not hardly any in the further in the past. And that makes me think that this graph got stretched dramatically toward the right. If you crunch the entire thing to the left, you end up with a sea level curve that's more consistent. In other words, the 30 million years is an artifact of there's something else going on. This is not something I would say is evidence, but it's an interesting.
Have we kind of dealt with coastal erosion? Is there anything more that we need to say about that? Have we?
Yeah, I think that's good for coastal erosion.
That's great. So I think what we should do is come back and talk about mountain erosion and river erosion and all those other things in a kind of part 2.
Yeah, sounds good.
So can we just kind of let's try and, at the conclusion of this episode, let's just try and sum this argument up. So if you were going to sort of sum it up in a nutshell for the layperson, give us the kind of coastal erosion argument for there being a time conflict with radiometric dating.
Coastal erosion is a process that happens on significant amounts of it happen on the scale of a human lifetime. And, any process that's going on at a few centimeters or a few inches or a few feet or meters per year, that's going to have just really profound effects in a million years, much greater in 100 million, a billion. And it really seems to me that these reconstructions of the history of the coasts don't really take into account this major factor. I think that's a mistake, and I think that when we actually start looking at it, as we saw, it may be hard to crunch exact numbers, but we can give it we can put very generous numbers in there. Numbers that favor the evolutionary scenario as much as we possibly can. And even doing that, the coastal erosion rates are so high that I don't think you can get the current morphology of the coast as it is and still posit millions of years of processes happening. That's
very interesting. So, guys, you're going to have to come back for part 2. Coastal erosion alone creates an enormous difficulty when we think about radiometric timescales, as we've seen in this episode. But there's more to come when we think about mountain uplift and some other factors. So you're going to have to come back for that in another part. So I'm not sure whether that will follow consecutively from this episode or whether it will be a future episode. But make sure you don't miss it and come back for part 2, where we continue this fascinating sort of deep dive into the processes of erosion and what it can tell us about Earth history timescales. Monte, thank you so much for being here with us today. Guys, we'll see you in a couple of weeks. Bye for now.
Thanks for listening to this episode of Let's Talk Creation. For more information, visit us at letstalkcreation.org, where you'll find an archive of past episodes and all our show notes. If you'd like to leave a comment or make a suggestion, you can find us on all the major social media platforms. Let's Talk Creation is brought to you in the U.S. by Core Academy of Science and in the U.K. by Biblical Creation Trust. As a listener-supported ministry, we are grateful for all of your financial support. Find out how you can make a contribution at our website, letstalkcreation.org. Also remember to like, subscribe, and share this episode with your friends. Thanks, and see you next time.